All right, welcome back to solving trig equations, but now it's going to require identities. Okay, you guys have seen these before, and we actually did derive them. I'm going to derive them again real quick for you. If you need more, after I go through the derivation, if you need more, okay, you can find it in your textbook on what the heck? That's not where I was going first. It is section 6.3. Okay, it's around page like 390, 392. But there's some that we already know. Okay, so we know the reciprocals, cosecant, secant, and cotangent. Those are considered fundamental identities. Okay, we also know that tangent is sine of theta over cosine of theta, and cotangent is cosine over sine. Okay, all of these we know. In fact, you've known them since geometry, I would dare say. Okay, the Pythagoreans are the ones that we generated, and that's these three. Okay, so that's what I'm going to do real quick for you again, just as a little refresher. So for the Pythagorean identities, I'm just going to put pi. If you think about your unit circle, right, and let's say not even the unit circle. Let's say that we are on a Cartesian coordinate plane, and we extend out to some point on a curve. Theta are reference angles at the origin, and we have a right triangle. Okay, well, on our unit circle, we knew that this coordinate was in the format cosine of theta, sine theta. So technically, this was our x and this was our y. Well, if we're going to look at our unit circle, I went back to unit circle, sorry, and we say that x squared plus y squared is equal to r squared, and if we're on our unit circle, well, x squared is cosine, so we have cosine theta squared plus sine theta squared is equal to 1 squared. Yep. And then we can just write sine squared theta plus cosine squared theta is equal to 1, and there's our first Pythagorean identity. Okay, hopefully this is bringing back some memories for you. That is number 1. I have this horrible tickle in my throat. Sorry, guys. And then to derive the other two, you simply divide. So let's say that I'm going to divide everything by sine squared theta. Okay, so that leads us over here. Well, sine squared divided by sine squared is 1. Cosine squared divided by sine squared is cotangent squared theta. 1 over sine squared is cosecant squared theta. Okay, so that brings us to our second Pythagorean. And I mentioned in class, I was on the side whiteboard, I mentioned in class that you can just remember sine squared plus cosine squared equals 1, and then derive the rest from there. Okay, and then if we divide by, I know this is really well laid out for you, by cosine squared, sine squared over cosine squared gives you tangent squared theta. Cosine squared over cosine squared gives you 1, and then 1 over cosine squared gives you secant squared theta. It is nice if you can remember all three. It's a little bit faster, I would say. And then it should be noted that you can move things around, and sometimes you'll need to. Okay, so if we have sine squared plus cosine squared equals 1, well, you can also have cosine squared theta equal to 1 minus sine squared theta. And sometimes you'll need this for proofs as we move along. Sometimes you'll need it from solving. And also, sine squared theta can equal 1 minus cosine squared theta. So as you start to get used to these, I would recommend that you have all these written down. I normally write the 3 at the top that are in red, and then I derive the rest just by moving pieces around. So the second Pythagorean, I would subtract maybe cotangent squared theta first. So 1 would be equal to cosecant squared theta minus cotangent squared theta. Or if I subtract the 1, then we get cotangent squared theta is equal to cosecant squared theta minus 1. It's all from the same Pythagorean, and truthfully it all stems from sine squared plus cosine squared equals 1, which stems from our right triangle drawn on our Cartesian coordinate plane. It's pretty rad how it all links together. And then for the last one, if we subtract tangent, we get 1 is equal to secant squared theta minus tangent squared theta. Or you could have, if you subtracted the 1, tangent squared theta equal to secant squared theta minus 1. And if you need to, if you don't know this already, please, 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 please write down that this has to be squared. None of these identities matter if they aren't squared. Okay, sine plus cosine does not equal 1. Okay, it's so important. I know I giggle, but it's so important. Okay, so there are your 3 Pythagoreans. We also have the even odds, which you guys need to know. We've covered these as well. The even odd identities have to do with the symmetry of the functions. Remember, if it's symmetrical across the origin versus if it's symmetrical across the y-axis and so forth. So this can be found on page 394 if you want a super in-depth, re-explanation. We did go through it in class on that side whiteboard. But as a refresher, the sine of a negative theta is equal to negative sine theta. Cosine of negative theta is equal to cosine theta. And then tangent of negative theta is equal to negative tan theta. All right, so again, page 394 if you want more in-depth. If you need more, sorry, there it is. If you need more in-depth, ask me. Okay, I'd be more than happy to do a separate video for you guys if we have a lot of people, or even if there's just one that needs that review. Okay, sweet. All right, so let's take a look at it. So the first one we have tangent of theta is equal to cotangent of theta. Now there's 4 bullet points up there. Definitely read through them. The last one's the most important for us for right now. Is just that each equation we're going to be asked to give 2 different types of answers. And basically what those 3 bullet points are saying is that now you might have to use the identities. Okay, so here we are, but definitely read through them, okay? All right, so tangent theta equals cotangent of theta. Definitely a few ways we could go about it. First thing that I'm going to do is I'm going to change it. And I'm going to change it to the sine of theta over the cosine of theta equal to the cosine of theta over the sine of theta. Now again, I'm going to say this a lot. There are numerous ways that you could attack these problems. Whatever you see, go with that. If you hit a wall and you can't go any further, then you need to stop, go back, and start over. All right. And then I have a proportion. So I'm going to cross multiply. That leaves me with a sine squared theta equal to a cosine squared theta. Well, since they're squared, I do know that I can use an identity. But let's say at the very beginning you decided to square both sides. Could you have used the identity then? Yeah, absolutely. Okay, we've got options. So I'm going to change sine squared theta to be, notice, this guy. So I'm going to change sine squared theta to be 1 minus cosine squared theta, and that's equal to cosine squared theta. I now have one trig function, which is great because if you have numerous, like at the beginning, tangent of theta equal to cotangent of theta, whoa, I'm going to have to do a lot of kind of guess and checking, right? If they're all the same trig function, it's a lot easier for us. So I'm going to get my cosines on the same side. So I just add it. So 1 is equal to 2 cosine squared theta. I can do that because they're both squared. And then if I divide by 2, I end up with cosine squared theta is equal to 1/2. Now, cosine squared theta is the same as cosine of theta squared. I'm trying to solve for theta, so I'm going to take the square root of both sides. That means that the cosine of theta is equal to plus and minus the square root of 1/2, which we know the square root of 1 is 1, and the square root of 2 is the square root of 2, but then we would rationalize. So we are solving the cosine of theta for plus and minus rad 2 over 2. If you need to see it, it becomes this, and then we rationalize. So we get plus and minus rad 2 over 2. That's my sloppy, sorry, work for you. Okay, so we're solving for theta, which means we're going to have to use the inverses. So cosine inverse of a positive and a negative rad 2 over 2. Okay, we're supposed to give 2 answers. So the first thing I'm going to do is list them between 0 and 2 pi. Well, rad 2 over 2 for cosine is a 45-degree angle. My interval is in radians, so that means I'm going to give my answer in radians. So that means, I should do theta equals. Let's stay consistent. So theta equals pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Okay, so that's the first type of answer. Now, the next one is for all possible theta. And I noticed that they're all separated by pi over 2 radians. You may see that, you may not. If you need to list out 4 answers and do plus 2 pi k for each of them, that's fine. I'm choosing not to. I'm going to say plus pi over 4. What? No, pi over 4 plus pi over 2k, where k is any integer. So that is my myriad of answers, my infinite amount of answers, and it is included in there. Sweet. Okay, so for that one, we didn't use any of the fancy Pythagoreans or the even odds, but we did get to use tangent equaling sine over cosine and cotangent. Okay, for number 2, I see that I could use that even odd identity. So I'm going to change sine of negative theta to be negative sine theta. And then that's going to be the cosine of theta plus sine theta is equal to 0. So I'm thinking to myself, man, cosine of theta plus sine theta equal to 0. Well, 1 and negative 1. Well, let's just keep going algebraically. I'm going to subtract it to the other side. Okay, so cosine of theta equal to the negative sine theta. And then I'm going to square both sides because I know I can use my Pythagoreans. Again, this is just one way that I saw it, that I'm going about it. If you know that cosine of theta plus sine theta equals 0, you can solve it from there. That's great. This is just my suggestion. So I have cosine squared theta is equal to sine squared theta. And I'm going to use one of my Pythagoreans. Oh, we did use the Pythagorean on the previous one. Sorry. And let's go ahead and change cosine this time. So we have 1 minus sine squared theta is equal to sine squared theta because of our Pythagorean versions. You can do either. Okay, it's not going to matter. So 1 equals 2 sine squared theta. And then sine squared theta is equal to 1/2. Come on over. And then I'm going to have the sine of theta equal to plus and minus the square root of 1/2. So sine of theta is equal to plus and minus rad 2 over 2. We're looking for theta, so we're going to have to apply that inverse. So inverse sine of plus and minus rad 2 over 2. So then if we were to solve for plus and minus, we get the same as what we did for the first one. But let me ask you this. Do they all work? If I were to plug in pi over 4, right? The cosine of pi over 4 is rad 2 over 2. If I plug in pi over 4, the sine of negative pi over 4 is a negative rad 2 over 2, which doesn't give us 0. This one doesn't work. What about 3 pi over 4? If I plug in 3 pi over 4, the cosine of 3 pi over 4 is a negative rad 2 over 2. What about the cosine of the sine of negative 3 pi over 4? Well, we'd be in the third quadrant. Sine is negative. That one works. What about 5 pi over 4? Nope. But 7 pi over 4 works. It's really important that you check your answers. Okay, so please, please, please get in the habit of checking your answers. We can see that these are separated by pi, so you're more than welcome to write 3 pi over 4 plus pi k. If you want to write them out each individually plus 2 pi k, that is totally fine. Now, for those of you that maybe didn't square both sides, you will come out with just those two answers, okay? It's because of the squaring that we have extraneous solutions. We create extra solutions. So yeah, definitely make sure that if you are squaring in your solving, that you check your answers because you're doubling the possibilities of the results. All right, sweet. Let's look at number 3. And if you need to, write that down. Okay, so for number 3, we've got cosine squared of theta minus cosine theta equals 2. Some people might want to factor out the cosine of theta, but we can't because it's not equal to 0. So important that you set it equal to 0 and then analyze from there. So cosine squared theta minus cosine theta minus 2 is equal to 0. It is a quadratic. I'm just going to factor it as is. I'm not going to use the substitution. So what can multiply to negative 2 and add to negative 1? Negative 2 and 1. So this factors out to be the cosine of theta minus 2 times the cosine of theta plus 1 equal to 0. We can set them each equal to 0 and solve them individually because of our zero product property. So cosine of theta is equal to 2 for our first one. So what's the inverse cosine of 2? For those of you that said there isn't one, nice job. Cosine and sine with their side ratios have the hypotenuse in the denominator. The hypotenuse is the largest side of a triangle. Always a right triangle. Always the largest. So this doesn't exist. No solution. You can't have it greater than 1. Now, if we were to try and find the inverse cosine of negative 1 between 0 and 2 pi, and in case I didn't mention it, because it states that it's 0 to 2 pi, we're not applying the restrictions. Okay, remember I've always said use the restrictions unless otherwise stated. This is that otherwise stated situation. Okay, so theta is going to equal pi, and then theta is going to equal pi plus 2 pi k, where k is any integer. Is any integer. I'll just box them together. Nice. Yeah, the cough is driving me batty too. Sorry, guys. Okay. So this next one, we've got sine squared theta equals 2 cosine theta plus 2. Right away, I see that I have a sine squared and a cosine theta. I need to try and get them to be the same trig function, so I'm going to use the Pythagorean again. I'm going to substitute 1 minus cosine squared theta in first sine squared, and that equals 2 cosine theta plus 2. Okay, here I see that I have a squared cosine, I have a singular, and then I've got constant. So I'm going to get everything on the same side to see if I can factor potentially. I'm going to subtract 1 to both sides, and I'm going to add cosine squared to both sides. So 0 is equal to cosine squared theta plus 2 cosine theta plus 1. So I need to multiply to 1, but add to 2. Again, I'm not using the substitution. If you want to, if that is easier for you, and then put the, where we used x to, we set cosine of theta equal to x, you can do that. That's fine. Please don't feel like you can't. Okay, so here we have the same factor. Cosine theta plus 1 is equal to 0. So cosine of theta is equal to negative 1. Theta is equal to the inverse cosine of negative 1. So theta is equal to, again, pi. And it could be pi plus 2 pi k, where k is any integer. Any integer. Excellent. Nice. Okay, we've got 2 more. Hope you guys are still hanging in there with me. For this one, we have secant, tangent, and cotangent. Whew, it's a lot going on. What I'm going to do is I'm going to change them. I'm going to change secant to be 1 of cosine over cosine theta. Remember, lots of options. This is just what I'm going to do. Equal to sine theta over cosine theta plus cosine theta over sine theta. Okay. I could move some things, but I think what I'm going to do is combine the right-hand side. So 1 over cosine theta is going to equal to, I'm going to get common denominators. So sine over cosine, I'm going to multiply by sine theta over sine theta. So I get sine squared theta over cosine theta sine theta. And then on the right-hand side, I'm going to multiply cosine theta over sine theta by cosine of theta over cosine of theta. So I get cosine squared theta over cosine theta sine theta. In doing this, I'm able to combine the fractions, which is nice. So I get sine squared theta plus cosine squared theta all over cosine theta sine theta Ha 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 ha. Our original Pythagorean, sine squared plus cosine squared, is equal to 1. Okay, so I'm going to state that 1 over cosine theta is equal to 1 over cosine theta sine theta, which I can break up to be 1 over cosine theta, which is secant theta, and then 1 over sine theta, which is cosecant theta. Huh, not bad. Now, they're not the same, I understand that, but if I subtract secant theta to the other side, it's now equal to 0, and I could factor out a common factor and go from there, which in this case is secant of theta. So I'm going to factor out secant theta. I'm left with cosecant theta minus 1 is equal to 0. And now, because of the zero product property, I can set each of these equal to 0 and solve individually. Okay, for the first one, I've got theta equal to the inverse secant of 0. Well, secant's the reciprocal of cosine. So ultimately what I'm looking for is the inverse cosine of 1 over 0. Is that possible? Is cosine ever undefined? No, it is not. So that is not possible. For the right-hand side, cosecant theta is equal to 1. So theta is equal to cosecant inverse of 1. Cosecant is the reciprocal of sine. So where is sine 1? At pi over 2. And then we're going to say pi over 2 plus 2 pi k, where k is any integer. Nice. All right, hang in there. We're almost done. We've got one more. And this is great because this is what we were just working on. Cosine of 2 theta is equal to rad 3 over 2. So we're going to solve for 2 theta. And we're going to find the inverse cosine of rad 3 over 2. Okay, cosine is positive in the first and fourth quadrant. So that means that 2 theta is going to equal pi over 6 plus 2 pi k and 11 pi over 6 plus 2 pi k. Because there's that value being multiplied to the angle, being multiplied to theta, we know that the period's going to change. So that's why we're writing it out as such. And then divide everything by 2. So theta is truly pi over 12 plus pi k. Everything's being divided. And 11 pi over 12 plus pi k. Okay, so this is where k is any integer. This is for all rotations. Any integer. Okay, now what we're going to do is we're going to list out the ones that exist between 0 and 2 pi. So since our denominator is 12, we can't go past 24 pi over 12 because that would be going beyond 2 pi radians, beyond those rotations. Okay, so theta is equal to, let's do the first one, which is pi over 12. If I add pi to that, I'm adding 12 over 12. So that would be 13 pi over 12. If I add another pi, that gives me 25 pi over 12, and that is beyond, so that is not included. The next one that we have is 11 pi over 12. If we add pi, that's 12 over 12, so that is 23 pi over 12. And that's one right before 24, so I'm done. Yeehaw! So it's not a whole lot different than what you guys have done in the past. Oh, look at all those colors. It's just knowing the identities, having them with you. And again, if you want a clearer, another video, we'll say, for the even odd identities, if you don't remember what we did in class, just let me know. All right, fantastic.